If I were to ask you right now, who actually invented the modern computer? What names immediately pop into your head? Maybe Alan Turing? Or, maybe you jump straight to the Silicon Valley pioneers like Bill Gates or Steve Jobs. Well, what if I told you the blueprint for the entire digital age wasn't drawn up in some pristine California garage or a top-secret World War II bunker? No, it was actually conceived in the smog-filled, steam-powered streets of 19th century London. I know, it sounds completely like science fiction, but it is absolute historical fact.
Welcome to This Explainer. Today, we're diving deep into the life and the staggering genius of Charles Babbage. He was a 19th century English polymath, a mathematician, philosopher, engineer, and quite frankly, the true architect of the digital age. I mean, long before anyone even knew what an electron was, Babbage designed the complete ground-up foundations for modern computing. So let's unpack exactly how this guy managed to look a full century into the future.
Okay, let's look at our roadmap for today. We're going to cover the human-computer problem, the difference engine, the analytical engine, his blueprint for modern computing, programming with punch cards, and finally, why he was a century ahead of time. Let's dive right in.
Starting off with Section 1, the human-computer problem.
To really grasp Babbage's solutions, we have to put ourselves in his world for a second. Think about the 1800s. International trade, navigation, major engineering projects, banking, all of it relied entirely on printed mathematical tables. And back then, a computer wasn't a sleek machine on your desk, it was an actual job title. Human computers sat there and calculated these massive tables entirely by hand. And look, humans get tired, right? We get bored, we get distracted. So, naturally, these tables were absolutely riddled with errors. And an error in a navigation table wasn't just a tiny typo, it could literally cause a ship to crash and sink. So the story goes that around 1812, while studying at Cambridge, Babbage is staring at these incredibly flawed logarithm tables, just pulling his hair out in frustration. And he has this absolute light bulb moment. Why not take the Industrial Revolution's whole concept of mass production and apply it directly to arithmetic? A mechanical computer would be infinitely faster and, critically, perfectly reliable.
You can actually see the rapid evolution of this vision right here. In 1812, he gets that initial spark of frustration with human error. Just a decade later, in 1822, he's already prototyping his first mechanical solution. And then boom, by 1837, just 15 years after that, he had finished designing a program for a fully realized general-purpose computer. Honestly, it's a stunningly fast intellectual leap from saying, I want to build a better calculator, to designing a machine that could theoretically process any logical problem you throw at it.
Moving on to Section 2, the difference engine. Think of this as version 1.0.
Now, this machine was powered entirely by a hand crank, not electricity, but the real genius here is how it worked completely without human intervention once it got going. Babbage used this mathematical trick called the method of finite differences. I promise we won't get too bogged down in the math. But basically, it's a very clever way to calculate extremely complex polynomial equations using literally nothing but addition and subtraction. Why is that such a game changer? Well, because building mechanical gears that can add and subtract is relatively straightforward. But trying to build gears that can multiply and divide, that is an absolute mechanical nightmare. So by relying on finite differences, Babbage designed a machine that could just automatically crunch massive numbers in sequence.
But here's the catch. Babbage's difference engine number 1 was never actually finished while he was alive, and when you look at these specs, you immediately start to understand why. Just consider the mind-boggling physical scale of this thing. It called for roughly 25,000 precisely machined parts. It weighed 15 short tons, that's about 13,600 kilograms, and stood 8 feet tall. It is just wild to juxtapose this massive room-sized brass behemoth against the microscopic silicon chips we carry in our pockets today. Babbage was out here trying to build a computer out of heavy brass and steel.
All right, Section 3, the analytical engine. This is where things get truly revolutionary.
So while he's working on that massive difference engine, Babbage realizes something crucial. A simple calculator just isn't enough. He makes this massive conceptual leap from mechanized arithmetic, just crunching specific numbers, to a fully fledged general-purpose computer. And it's this specific leap that is exactly why he's recognized as the father of the computer today. The analytical engine wasn't designed to solve just one specific math problem. It was designed so it could be given instructions to solve literally any problem.
Section 4, blueprint for modern computing. Let's look at the anatomy. This right here is the absolute core of our explainer today. We can map his 19th century design perfectly to whatever device you are using to listen to this right now. Let's rapidly fire through these. The analytical engine separated the data memory from the program memory. It used instruction-based operations. It had a control unit capable of conditional jumps, meaning the machine could actually make decisions based on its previous calculations. It had sequential control, looping, and a completely separate input and output unit. Babbage called his memory unit the store and his processing unit the mill, kind of like a textile mill processing threads. Today, obviously, we call the store our RAM or hard drive, and the mill is our CPU. His structural anatomy is literally the exact architecture we are still using over 150 years later. It's crazy.
Section 5. Programming with punch cards. Time to talk about software.
Now, a machine is basically just heavy metal without a way to give it instructions, right? So to feed commands into his engine, Babbage openly borrowed a really cool concept from the textile industry, the jacquard loom. These looms used stiff pasteboard punch cards to automate complex weaving patterns. And Ada Lovelace, who is a brilliant mathematician and a very close collaborator of Babbage, perfectly captured the poetry and the sheer power of this concept in this quote. She realized that the numbers inside Babbage's machine could represent way more than just quantities. They could represent logic, music, letters. She famously said, "The machine weaves algebraic patterns, just like the loom weaves flowers and leaves." She completely hit the nail on the head.
Now, Babbage himself actually wrote a series of programs for his engine between 1837 and 1840. But Ada Lovelace is historically celebrated because she published an incredibly detailed algorithm designed to let the analytical engine calculate a complex sequence known as Bernoulli numbers. Because of this beautifully documented work, she's frequently described today as the world's first computer programmer. Together, Babbage and Lovelace had essentially mapped out the entire modern discipline of software engineering before a single fully working computer was even built.
Which brings us to our final section, Section 6, a century ahead of time.
So this begs the question, why didn't the Victorians have an internet? Well, the real tragedy of Charles Babbage is that he died in 1871 without ever seeing his great analytical engine fully realized. He ended up losing his government funding, which was a massive $17,000 at the time, mostly because of continuous delays, his habit of constantly tinkering with new designs instead of finishing old ones, and huge personality clashes with his chief engineer. So for over a century, historians kind of wondered, was Babbage just a madman, or were his designs actually sound? Well, in 1991, the Science Museum in London finally decided to find out. Using his original blueprints and strictly limiting themselves to 19th century manufacturing tolerances, they built a functioning difference engine. And guess what? It worked flawlessly. It returned results perfectly to 31 digits. By 2000, they even finished his automatic printer. It proved definitively that his mechanical engineering was completely perfect all along. It was just the Victorian manufacturing infrastructure that couldn't keep up with his brilliant mind.
I want you to think about the number 675 for a second. Today, there's actually an ongoing project called Plan 28, and they're aiming to finally build the complete analytical engine. Experts have analyzed the plans, and they estimate that this massive, brass, steam-powered behemoth would have a memory equivalent to just 675 bytes, and it would run at a processing speed of about 7 Hz. Now, when you consider that the smartphone in your pocket has billions of bytes and runs at gigahertz speeds, 675 bytes sounds incredibly, almost comically small. Yet those 675 bytes contained the entire foundational logic for the modern world.
So I want to leave you with this final, lingering question to ponder. We've seen that his logic was completely flawless. We've seen that his architecture is literally still in use today. His concepts of hardware and software were entirely complete. A single human mind was quite literally a full century ahead of human manufacturing capabilities. So if Charles Babbage had just possessed the precision tools of a few decades later, how much sooner would our digital age have actually begun? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.